Hello and welcome to another lecture. In this lecture, we're going to design a reinforced concrete shear wall. Let's do this problem. The wall we're going to design is a 3,000 pound concrete. It really should be 4,000, but steel is about 60,000 psi. The wall is about 14 feet tall and 10 feet long. And the shear value of sideways, either earthquake or a wind, has about 240 kips a pushing on it. Now, the thickness of the wall sometimes is limited if the architect has determined it, or if you don't have it, you can assume it, or we can just use ACI 11.3.1. Basically, H is equal 1 over 25 times the length. Let's just assume 8 inch for now. That's what it comes out to. All right, let's get to work. And all right, we're going to go ahead and check the wall thickness, but there's something interesting I want to show you between the ACI 318.14 and 318.19. And you get the same value, basically. The AC, for checking the wall thickness, section 11.5.4.2, it says the equation is right here. Use H times LW. But if you go into ACI 318.14, it says phi times 10 times square root of F prime C, but HD, not H times LW. But however, D is equal to 0 times 8 LW. So, which is basically 96 inch. But if I calculate the shear based on ACI 318.19, I get 315.5 kip. Let's look at the ACI, what I'm talking about right here. This is the 11.5.42. It says VN or VU at any horizontal section shall not exceed this number. Then in a commentary explains why they made that choice going from 314 to 319. Instead of a H time D, they're going to use H time LW, which is basically the area of this ACV. And if we look at the 14, it says right here. That's all it says, this one line right there. So let's go back to writing here. If I use the 14, VU is equal phi, which is 0.75, times 10 times square root of 3,000 times 8 times 96, get the exact same answer as above. Anyway, so that number, 315.5 kip, is bigger than our shear, which was 240 kips. We are okay with that thickness, so we're going to stick with that thickness. Use 8 inch. We're good there. All right, next we're going to go ahead and compute VC, and that's per ACI 11.5.4.6. If we look at that code, here's the code right here. I don't know where they moved it to in 318.19, but we're going to go ahead and use this equation and this equation. And it says for tension and compression, lesser of these two value. So we go ahead and do this two value. And then down here says, equation shall not apply if mu over VU minus L over W is negative. So I don't think so we're going to have that problem. But let's go back to the problem here. So what I did here, we calculated the first one, which is this equation right here, and this came out to be 138.8. Now we're going to calculate the next one, which is this equation right here, but we have to find out what is mu and VU is. VU we know what it is, and let's calculate mu, but we have to calculate it at the base of the wall, but the distance either 5 feet or 7 feet, but 5 feet control here. And we're going to say our VU, let me change color for good luck here. So our VU was given as 240 kip, and our MU is going to be 240 times, that'd be 14 minus 5, so it'd be 5 feet away, and that's going to be 2160 foot kip, or make it multiply by 12, it become 25,920 inch kip. So now we're going to go ahead and take this value, we're going to plug it right into here. So we're gonna get 156 point kip, and also we have the other one was the lesser of the two. So that's our mu, that's our VC. The other VC came out to be 138. So this one controls right here. So the next thing we're going to check, do we require shear reinforcement? Remember, we did this quite a bit when we did the shear design. Half of the VC should be less than VU. So half of a VC comes out to 5205, and our VU was 240 kips. And we say, yes, we need it. So that come out a yes. And so the horizontal reinforcement basically is the transverse anyway. So our number, if you remember, VU is equal phi times VC plus phi times VS. When we did that, we did quite a bit this. Or we could say, rewrite this, it'd be VU is equal phi times VC plus phi times A VFYD divided by S. And I believe that was ACI 22.5.1.1. So AV divided by S is equal VU minus phi times VC divided by phi times FYD. We plug that in, become 240 minus 0.75 times 138.8. Divide that by phi was 0.75. We're going to use 60 KSI, and our D was 96 inch. So that will give us 0.0315 inch. So now remember, when you have this number, our AV is a 2-bar cross-sectional area, because we have 2 layers of horizontal bar that we're going to place. And then we're going to say, okay, based on that, I'm going to say try number 3 bars, and S is equal, that's 2, because it's a 2 layer, times 0.11, that's the area of the number 3 bar, inch square, divided by 0.0, this 315, and that will give us 6.98 inch. And if we try number 4, our S is equal 2 times 0.2. 0.2 is the area of number 4, divided by 0.0315, and that gives us another option anyway, at 12.7 inch. Remember, you don't have to stick to this number. These are basically, there's a limit on maximum, minimum. And our maximum vertical spacing, our max vertical spacing of horizontal shear is per ACI 11.73.1. Let's look at that code right here. And the code is right here. It says spacing of S transverse reinforcement cast in place, it's got to be, shall not exceed 3 times H, 18 inch, or LW divided by 5. So we're going to try all this 3 of these, see which one is going to control. So let's go back to the writing here. We had LW divided by 5,
and that is 10 times 12, make it an inch, and divide that by 5. That will give us 24 inch. The second one was 3 times h, which was 3 times 8. That's also 24 inch. And the third one was 18 inch, which is basically is 18 inch. And this one controls the less of all these three. And now we know that, so we're going to find out rho of a transverse bar is equal AV divided by AS. And the area is basically the wall thickness times vertical spacing of the horizontal shear reinforcements. So our rho T, come on, is equal 2 times 0.2, and divide that by 8 times 12, and that gives us 0.00417. And this should be bigger than the minimum. Let's find out what the minimum requirement is. ACI 11.62. Let me if I can find that. It says rho T should be bigger than 0.0025. Right here. Should be at least that much right there. All right, let's go back to the writing here. So it's bigger than 0.0025. Then we're going to say, okay, use number 4 at 12-inch vertical spacing. Now we're going to go ahead and design the vertical shear reinforcement. That's for ACI 11.6.2. And let's take a look at that. And here it is right there. We're just going to set it equal. So it should be at least bigger than that, but let's set it up equal to this right here, 11.62. So this, now we're going to assume number 4 vertical bar. This is a 2-bar cross section. So we're going to say S is equal. And number 4 again is a 0.2 that area. This is the area number 4. That's in case you know where to come from. And time 8-inch wall thickness multiplied by 0.00342, and that gave us a 14.62 inch. Same spec, similar spec. We're gonna find out the maximum So we have two choices, LW divided by 3, which is equal 10 times 12 divided by 3, and that will give us 40 inches. Second choice is 3 times H, which is 3 times 8, that's 24. Or last one is 18 inch, which is equal 18 inch, and this again controls. Therefore, we're going to use 2 number 4 bars at 14 inch on center. This is horizontally, by the way. All right, so we're going to go ahead and design the vertical fluxual reinforcement. Let's first calculate our moment. Mu is equal 240 times 14 feet at the base of the wall. That's equal 33. 3,360 foot cube. This is a base of wall. And we remember this equation, mu divided by phi bd squared. So 3360. Let's convert that to a pound and make it an inch pound times 12 and divide that by phi was 0.9 for fluxual, and our B is 8 inch and our D is 96 square, and this give us 607.6 psi. So there's three different ways we can calculate the area of the steel. In a lot of textbook, you can go ahead and use this and go find rho, and rho is equal 0.0118. That's, you can find a table based on these moments. A lot of designer has this. Second way, you can go ahead and use AS is equal, minimum AS is equal 0.002 times the gross cross-sectional area, which that kind of you have to come up from there, do some trial error. Third one, which I'm going to use, we used in class before and it worked out well, is use AS is equal mu divided by 4D. So let's go this way first from the table. And you can go to a textbook and find that table. I don't think it's in ACI. If you know it's in ACI, let me know, please. So that will be, let's go this way. AS is equal rho times BD 0.0018 times, that's 10 feet by 12. 8 by 90, okay, 8 times 96. And that will give us a 9.06 inch square. Now remember, these numbers are conservative. If we use this one here, mu came out to be 3,360. It has to be in foot cube, by the way. 3,360, and divide that by 4 times 96. That gives us 8.75 inch square. Very similar. I think this is more closer than that one, but anyway, that's for another day. So now we can say, if you go to the table, we can say use, if we use 10 number 9, that will give us 9 inch square. At each end. Remember, view on a wall come from both sides. So that's, we assuming that way. Let's do the final result. Okay, here's our final drawing here, and we went a little bit conservative, which is okay. So now we had the number 4 bar on the outside right there, and then we had the number 10 on each end, 10 number 9 on each end, then we had the number 4 in the middle. This distance right here is basically as a cover, maybe 3.5 inches. So I got 3.5 inches on both ends, so that's 7 inches. We calculated the based on the length was D was based on a 0.8 times 120. But literally, if you take 120 minus 7 inches, and then calculate that way, you end up with a smaller bar.
So if this wall had the vertical load on it, also be a bearing wall plus shear wall, we really have to calculate the area of the fluctuator, and that'd be basically using the interaction diagram which we done before. But good luck, and hope you liked it.